Hai, salam sejahtera dan good afternoon everyone. Welcome to Pusat Tuisyen Akademi Youtuber with joint venture of eDidik Malaysia and Guru Malaysia. I'm Mr. Peh. Currently, I am teaching at College Tingkatan 6 Tempat Timah Melaka. I am the on-duty teacher for this week. For your information, Akademi Youtuber Malaysia is preparing for you 2 lessons of SPM Physics classes, which is the Form 4 classes will be held on every Friday, 9:30 p.m. And another class will be Form 5 SPM Physics will be held as usual today, which will be at 8:45 p.m. So today I am going to continue the chapter 5 topic electronic with the subtopic of 5.2 semiconductor diode. And to let you know, you may actually get the e-link schedule after the lesson, and you have to fill in the link within the 30 minutes just for the lesson finish at about 9:45 p.m. So without further ado, let us start our lesson today. So in today's learning standard, total you are going to learn today will be about 2. The first learning standard for today's lesson will be you need to able to describe the function of semiconductor diode. Okay, so firstly, you need to know the definition of the semiconductor. So what is a semiconductor? So here, this will be the definition. Okay, so it's a material which is properties of electrical conductivity located between the electrical insulator and electrical conductor. So that means that the electrical conductivity of the semiconductor will be better than insulator, but poor than conductor. And intrinsic semiconductor, so that means the natural semiconductor you may find surrounding us will be such as the silicon and germanium. So you may referring to our periodic table, and at the group 14, silicon and germanium will be the 2 of the example I mentioned just now. So besides that, you may look at the periodic table. The metalloid with yellow color is also others example of the semiconductor example. Okay, so the silicon and germanium will be derived its semiconductor properties from its own atoms. So here, as mentioned that the properties here we emphasize today will be the conductivity of electricity. So it will be between the insulator and conductor. And here is the process of semiconductor manufacturing. So the silicon where can be extracted from the sand. So the sand will be with the chemical formula as silicon dioxide. So the silicon able to extract from the sand, and it is the main material for the fabrication of wafer. Then, after the fabrication of wafer, the electrical circuit will be printed or integrated on the wafer, and dicing or saw become chips. So the chips is mainly used in camera, automotive, such as vehicles, wearable, and health and smart product. Okay, so how semiconductor conduct electric. Okay, so here the pure semiconductor act as an insulator when they are cold, but conduct a small current when they are at room temperature. Okay, so here we have Cikgu Hasnitah. So thank you for joining my lesson. Okay, so here just now we mentioned that the conductivity of semiconductor will be between the conductor and insulator. So here the semiconductor will be able to conduct electric when it achieves high temperature. So at the room temperature, which is about 25 to 30, so the current will be only small. The small current will be able to flow through the semiconductor. So why this? Because in cold condition, the outer electron in the silicon crystal, which all are involved in perfect covalent bond, leaving no free electron to conduct electricity. So here you can refer to this figure. So this is the structure of the silicon. So silicons from the group 14, it has 4 valence electron. Okay, so to achieve stable electronic configuration, so each electron will be joined with another electron from the neighbor atom will be here. So therefore, in cold condition, all the electron valence of the respective silicon will be bonded with the neighbor electron valence of the neighbor atom. So end up there will be no any free electron able to conduct electric. Okay, so but as the temperature increases, the energy will be gained by the electron and able to break free from the covalent bond. Okay, so this is a covalent bond where bonded between 2 valence electron, between 2 electron here, between 2 atoms of silicon here. Okay, so here you can see from this figure, there will be some of the electron will be break free from the covalent bond. Okay, so here, the break free electron we know as a conduction electron. Then you may see here, we have an empty space where because of the conduction electron break free from the bond, and here we leave a hole. Okay, so which is less negative and we know as a valence hole. Okay, so here, through this figure, so there are 2 carrier is produced where it will be conduction electron, where it will be negatively charged, and another one there will be positive carrier, which is a valence hole. Okay, so here, as mentioned, the carrier, the charge carrier presence for the semiconductor at higher temperature will be free electron, will be this, where the free electron come from the back free of the covalent bond. And the empty space where leaving by the electron will be known as hole. Okay, so when a potential difference is applied across an intrinsic semiconductor, it conducts a very small current. So here you can look at this figure. So the semiconductor is connected with battery, where is the potential difference mentioned in sentence 5. Okay, so this may cause the flow of the electron and also the hole. So the movement of the electron and hole is in opposite direction and cause the current will be produced. Okay, so look at sentence number 6. Conduction in semiconductor is by the means of movement of the free electron and hole in opposite direction. So in this figure, you can see the dashed line is the motion of the hole conduction. So which is a hole here lah. So it's moving at the right direction, while the black dot showing or represent as the electron is moving to the right side. So when there is a flow of electron, the current will be produced. Okay, so the next here will be the doping process. Okay, so what is the doping process? So the definition is stated in the first sentence here. So the doping is a process of adding a certain amount of specific impurities called dopants to the pure semiconductor to increase its electricity conductivity. Just now we mentioned already, the pure semiconductor, we have the example of silicon and germanium. So both will have a free electron and hole at the high temperature. But the numbers of hole and the electron is actually not very much. So the numbers of electron and hole able to increase by adding dopants to the pure semiconductor. Okay, so here this is a figure of pure silicon atom. Okay, so you can see here all of the silicon will be surrounded with 8 electrons. Okay, this is because the silicon itself, as mentioned, there will have 4 valence electrons, and the neighbor of the electron will have another 4 electrons. So when both electrons sharing the electron together, so there will be formed one pair of the bonding pair between the 2 silicon. Okay, and there will be no any extra electron will be present at the low temperature. Okay, so the free electron will be present at the pure semiconductor or silicon here when they are at high temperature. Okay, so here we have 2 type of the semiconductor will be formed after the doping process. So here we have an N-type semiconductor and a P-type semiconductor. Okay, so this depends on the type of the dopant atom added to the pure semiconductor. Okay, so here we have the first type of the dopants or impurities added to pure semiconductor or pure silicon here. So here we have the atom trivalence. So where the atom consists of 3 valence electron. So they come from the group 13 in the periodic table. So here we have an example of boron, aluminium, and gallium. So here you can observe the P semiconductor. Okay, so here we have the example of the dopants added by boron, so which is a trivalence atom and presence of the 3 valence electron. So you can look at this part. So where the boron is surrounded with 7 electron and 1 hole actually. So why here we have 7 electrons? Because the semiconductor, the pure semiconductor or silicon from the group 14 will contribute for 4 valence electron, and the boron itself have 3 valence electron. So end up there is an extra hole or the space without electron. So here will be the carrier we know as hole or the positive carrier here. Okay, so this side of semiconductor we know as a p-type semiconductor. P represent as a positive. Okay, so another type of the dopants here will be the pentavalence atom. So the pentavalence atom is come from the group 15, so where the atom's presence of 5 valence electron. So the example of the pentavalence electron here will be phosphorus, arsenic, and antimony. Okay, so these are 3 type of the pentavalence atom example. So here you can observe the N-type semiconductor. So the pink color atom here showing the atom of phosphorus. So as mentioned, the phosphorus is come from the group 15. So it has 5 valence electron. 1, 2, 3, 4, 5. So another 4 valence electron is come from the pure semiconductor or silicon here. So if you look at this part, you may see that the total electron surrounded with the phosphorus will be 9. So here they will be have 1 extra electron, and the majority carrier for this side of semiconductor will be electron or negative charge. So here we know as a N-type semiconductor. So the N here represent as a negative. Okay, so here that means that through the process of doping on pure semiconductor, so through extrinsic semiconductor will be formed. So it will be P-type semiconductor, P-type semiconductor and N-type semiconductor. Okay, so here there will be the detailed comparison between two types of the extrinsic semiconductor we learned just now. Okay, so here the N-type semiconductor, as mentioned just now, it will be the negative type semiconductor. And the P-type semiconductor will be the positive type of semiconductor. Okay, so here, let us compare the difference between these two types of semiconductor. Okay, so for the N-type of semiconductor, as we mentioned just now, the N here represent as a negative. So the majority carrier here will be the electron. Okay, so it will be have an extra electron or the majority carrier as electron in this type of semiconductor. Okay, so the semiconductor which is electrical conductivity contributed by free electron as a majority charges carrier, and hole will become the minority charge carrier. So you can see here from figure. So we're using the pentavalent atom as our dopants in the doping process. So end up they will be have more electron in the N-type semiconductor. On the other hand, the P-type semiconductor here will be adding with the trivalence atom or the dopants from the group 13, which presence of the 3 valence electron. Okay, so the semiconductor which is electrical conductivity is contributed by hole as majority charges carrier and free electron as minority charge carrier. Okay, so again, you may look at the blue color atom. Here will be the trivalence atom. For example, just now we have the example of aluminum or boron. Okay, so the presence of 3 valence electron. So here will be 3 valence electron belong to the trivalent atom, and then another 4 electron will be come from the pure silicon. So here there will be an empty space where is less negative and we know as hole. Okay, so here for the P-type semiconductor, so the major carrier here will be the hole or the positive charge. Okay, then next, there will be the checkpoint question. Okay, so here we have already finished the discussion regarding the two types of semiconductor, the P-type and N-type, through the process of doping in the pure semiconductor. Okay, so let us check your learning progress through the question here. Okay, so the adding of impurity into pure semiconductor material. Okay, so what is the process we know as? So here, A will be doping, B rectification, C amplification, D the muonic emission. Okay, so I think the answer is very clear. Okay, so however, I discussed with you all the terms here for the all option here. So the doping is the process of adding an impurity into the pure semiconductor material. The answer should be A, right? What we just learned, the terms here. Okay, and then the B rectification is actually function of the diode, where we'll be converting the AC current to DC current. Okay, so hi Jimmy. So welcome to my lesson. Okay, so thank you for joining my lesson, and you may show your answer together with me in the chat room so that I know you are learning together with me here. Okay, so here the rectification, this definition will be introduced later on at the learning standard 2. Okay, and then the amplification is a function of the transistor where will be amplified the current. And this term will be C at this chapter, but at the subtopic of 5.3. Yeah. Okay, so very good. Okay, so the answer from Jimmy is doping. Good. This is the answer for this question. Okay, so here the last term here, the thermionic emission is the process where heating the metal surface and emitting the electron so that it may produce a cathode ray. Okay, so this one will be learned already at the chapter 4, actually chapter 4. Subtopic of 5.1, this chapter, but subtopic of 5.1. Okay, so here the answer is very clear. This is A, where is given by Jimmy also. Let's say group try Jimmy. Okay, so for question number 2, you may also share your answer together with me here at chat room. Okay, so let us read the question first. The doping process of pure semiconductor with pentavalence will. Okay, so here we have the option. Cause the semiconductor to be negatively charged, produce p-type semiconductor. Cause the resistance of semiconductor to increase, produce majority charged carrier, which is electron. Okay, so here, what is the answer here? Okay, so the pentavalence elements or atom, actually, we just go through just now. So here we'll be referring to the atom from the group 15. So there will be have 5 valence electron. Okay. So 4 of the electron will be form the covalent bond with the pure silicon, can be germanium also, and others pure semiconductor. Okay, and then one of the electron will be free to move through the pure semiconductor. So here the negative electron will be the majority carrier, and it will be form the N type of semiconductor. Okay, so answer from Jimmy is A. Is it A, Jimmy? So we must choose the best answer here. Okay, so here for the first one, cause the semiconductor to be negatively charged is actually B. Actually, the A is wrong because the doping process is just increase the hole or electron. Okay, if I say in this case, when we're using the pentavalence atom, so actually the major carrier, it will be electron. Okay, it will be electron, and this may form the N type of semiconductor. Okay, so the first is actually wrong already. Okay, so because it's not changed the charge of the semiconductor, it's actually add on electron in this case now for pentavalent elements here. Okay, then the second, it will be form N type of semiconductor because the major carrier here, it will be electron. Okay, so P here referring to positive now. Okay, so when we have the doping process, in this case, it will be have more extra electron. Okay, so the resistance will be decreases actually, not increase. So the answer here should be D, Jimmy. Okay, so the major carrier here will be electron because we have 1 extra electron. And others 4 will be form covalent bond with the pure semiconductor. Okay, so here answer should be D, Jimmy. Okay, so the next question. Question number 3. Okay, so which of the following diagram is an N-type semiconductor? Again, N-type referring to negative type of semiconductor. So the major carrier here, it will be electron. Okay, so which will be the answer? Okay, so you may also show your answer in the chat room. Okay, so here, as mentioned, the N-type of semiconductor, it will be have one extra electron as a carrier in the semiconductor here. And add on the pentavalent atom, which has a 5 electron valence, one extra electron will be as carrier, another 4 it will be form the covalent bond with the pure semiconductor. So here can be silicon or germanium. Okay. Okay, so here silicon or germanium is a pure semiconductor. So you can see all the option here. We have the major atom of Si and Ge. Actually, is referring to silicon and germanium. Okay, and then the boron, okay, from option A, gallium from the option B, and then the indium from the option D is actually from group 13. Let's say you can just look at the periodic table. Okay, so boron, aluminum, and gallium come from group 13. So they are the trivalent atom. Okay, so it will be form major carrier as whole, as they will be lack one of the electron. Okay, so they will be form P semiconductor, but not the N-type semiconductor. Okay, so here, answer very clear, they will be not A, B, and D. Okay, so for C and S is arsenic. They are actually from group 15. Okay, so I also shattered with the green color box already in the periodic table. Okay, so they are from group 15. And you can see there is a extra electron just besides the arsenic. Okay, so the answer here is very clear. It will be C. Okay. Okay, so after discussion for the N-type and P-type semiconductor, okay, so now we need to relate the type of semiconductor we learned just now to semiconductor or diode. Okay, so how the diode is formed? Okay, so here, the definition of diode will be like this. A diode is a device that allows electric current to flow in one direction only. Okay, so you can look at the figure here. This is a symbol of the diode. Okay, so the anode will be at here, and then the cathode will be in front of the triangle. Okay, so that means that the diode is a polar device. You should connect it to correct terminal. Okay, when you connect or joining all the circuit, electrical component in the circuit. Okay, so semiconductor diode can make by joining pieces of N-type and P-type semiconductor. Okay, so just now we know already. Okay, so how the N-type and P-type semiconductor to form. Okay, so where the N-type semiconductor, the main carrier, it will be free electron. Okay, so here this is an N-type semiconductor. For P-type semiconductor, is a positive type of semiconductor. So the major carrier here will be hole, which is a positive charge. Okay, so this is a P-type semiconductor. So the diode will be able to make by joining the P and N-type of semiconductor together. Okay, so here the semiconductor diode is also known as a PN junction diode. So you can look at this figure. So the diode is have another names where we can know as a PN junction. Okay, so the region of the P type and the N-type semiconductor are called anode and cathode respectively. Okay, so here the P-type semiconductor can also consider as a anode, where you can just look at this symbol. Then the cathode, they will be for the N-type of semiconductor here. Okay, so here there is a layer we know as a depletion layer in the diode, where there will be between of the P-type and the N-type semiconductor. Okay, so it will be these parts where I box with red color line already. Okay, so when a P-type semiconductor material is in contact with an N-type semiconductor material, a layer called depletion layer is formed in the middle, will be this. Okay, so in this junction, okay, besides we can know as a depletion layer, or now we can also call it as a junction. So where between the P-type and N-type semiconductor. Okay, so here from this figure, you can see the arrow of green color is moved from the P-type to N-type. Okay, so here is actually the movement of the hole from the P-type semiconductor drift to the opposite side to a direction of the N-type semiconductor. So that means the hole will be across this depletion layer. Okay, then the electron, you may look at the red arrow here, is a movement of the free electron from the N-type semiconductor to the P-type semiconductor. Okay, so the sentence will be like this. Electron from N-type semiconductor drift across the junction to fill in the hole in the P-type semiconductor. So that means here, the junction is just like the middle layer between the P-type and N-type semiconductor. Okay, so when the energy provided is enough, so the electron will be moved from the N-type to P-type semiconductor. On the other hand, the hole will be moving from P-type semiconductor to N-type semiconductor. Okay, so as a result, the depletion layer become narrow. Okay, so here, number 4 is a very narrow region. So it will be this depletion layer. Okay, so which has lost all its available free electron and hole, and thus behave almost like a pure silicon with high resistivity. Okay, so you can see here, this will be the narrow region where we know as a depletion layer. Okay, so when the movement of the electron to the P-type semiconductor and the hole to the N-type semiconductor, at one of the moment, so the depletion layer will be not allowed or cause the repulsion for the electron to jump again from N-type to P-type semiconductor. There will be also for the hole. Okay, will prevent from the motion from P-type to N-type semiconductor. So here there will be no any electric current will be produced now. Okay, so any further movement or charges across the boundary in the depletion layer will be repelled by charges in the layer. Okay, so you can see from the figure. So here, this is a negative charge already. Okay, so the electron will be repelled when they want to try across the depletion layer. They will be same for the hole. So be repelled by the positive layer here. Okay, so the layer of negative charge in the P-type semiconductor will be here. Will prevent the majority carrier from the N-type region, which is electron, from crossing the boundary. Okay, so here the electron will be not able to move anymore. For the hole and the p-type semiconductor, the positive layer, okay, so this positive layer will be also prevent the hole from closing to another side. Okay, because both have the same charge. Okay, so here we prevent major carrier of the p-type region, which is a hole crossing boundary to opposite side. Okay, so that means when depletion layer become narrow and narrow at certain value, okay, so the free electron will be not able to cross to opposite p-type semiconductor. There will be also for the hole. Okay, so this will result the potential different acting from n-type material to the p-type material across the junction. Okay, so this potential difference we know as junction voltage. So with this. Okay, so in normal condition, the PN junction deliver no current since the charges are in equilibrium. That means here you can see at the depletion layer, there will be have a positive charge layer at the side of the p-type semiconductor. Then there will be negative charge layer where will be just beside the p-type semiconductor. So both these layer will prevent the respective charges or carrier to close the junction here. Okay, so the current will be not able to flow since there will be no any flow of the carrier here. Okay, so this junction voltage prevent charge carrier from drifting across the junction, as I mentioned just now. Okay, so the junction voltage for germanium and silicon are approximately 0.1 volt and 0.6 volt. Okay, so here you can just observe the graph. So this point will be referring to the 0.1 volt. And then this point will be referring to 0.6 volt. Okay, so you can see here, the current will be 0. And these two voltage. Okay, so where we know as a junction voltage. Okay, so to allow the current flow through, the voltage of the source of the energy provided to the diode must be greater than 0.1. If I say the diode material we use is germanium, for material use as silicon, the minimum voltage provided must be greater than 0.6 volt, so that the electron will be able to cross the junction. Okay, so here, this will be the operation of the diode, as what I mentioned just now. So to allow the electron on the hole to closing the junction. Okay, so the energy provided must be more than 0.1 volt or 0.6 volt if using germanium or silicon here. Okay, so there will be have two methods for the operation of diode, which is the forward bias and reverse bias. Okay, so for the forward bias, so the P is connected to positive. Okay, so here will be the p-type semiconductor will be connected with the positive terminal of the battery, while the n-type semiconductor will be connected to the negative terminal of the battery. Then on the other hand, the reverse bias will be the n-type semiconductor will be connected to positive. And then the p-type semiconductor will be connected to the negative terminal of the battery. Okay, so what will be the effect for the two method of the operation of diode. So we discuss here. Okay, so here will be discussion for the different or comparison between the forward bias and reverse bias of connection of the diode. Okay, so as per mentioned just now, so for forward bias, the p-type semiconductor of the diode will be connected to positive terminal. Okay, so here P region will be p-type semiconductor. Positive will be connected to positive terminal of battery. Then for the N region or the N-type semiconductor, it will be connected to the negative terminal of battery. Okay, so on the other hand, for the reverse bias, okay, so the P-type semiconductor will be connected with terminal negative of battery. Then for N region or N-type semiconductor, it will be connected with the positive type of semiconductor, positive terminal of the battery. Okay, so this will be the difference between the connection of forward bias and reverse bias. Okay, so here, as mentioned just now, so to allow the current to flow through, where to allow the electron or hole to closing the junction, so the current will be produced and the bulb will be light up. Okay, so here, the cell voltage is greater than the junction voltage. Okay, just how we mentioned already, for germanium, the junction voltage will be about 0.1. For the silicon, the junction voltage will be about 0.6. Okay, so here, the cell voltage referring to the voltage provided by the dry cell. Okay, so here must be greater than 0.1 volt. If the semiconductor we use is germanium, if the silicon is used as a material for semiconductor, so the cell voltage must be greater than 0.6 to allowing the carrier closing the junction, and the current flow will be cause the bulb to light up. And this will be known as a forward bias lah. Okay, so on the other hand, so the cell voltage is lower than the junction voltage. Okay, so here you can just look at the figure. Okay, so because the connection terminal of the diode and the terminal of battery is not in the same terminal. Okay, so here this will cause the depletion layer become wider. Okay, so the energy provided will be not able to let the carrier to closing the junction. So here the bulb will be not light up, and here will be known as a reverse bias lah, the connection. Okay, then here the next difference here will be the depletion layer. You can see for the forward bias connection, so it's narrow, so will be allowing more carrier to closing the junction. So the resistance will be decreases and cause the current flow and bulb will be light up. While for the reverse bias, you may see that the depletion layer, so the yellow color part is wider. Okay, so this is because of the electron from the N region is pulled away from the junction. For the hole, also the same, or we pull to another side. Okay, so causes the depletion layer become wider. Okay, so when the carrier is not able to across the junction, so the resistance will be higher. Okay. Okay, so number 4 here. Okay, so just how we mentioned, because of the PN junction or depletion layer is very thin, so the hole and the electron will be able to across the junction. Okay, so here will be produced large current to flow through the diode. Okay, so from X to Y. Okay, from X to Y. While from the reverse bias, because of the carrier is not able to cross the junction, so there will be no any current will be produced. Okay, so here for the forward bias, since there is a movement of electron or hole to another side or cross over the junction, so the movement of the carrier causes the current to flow and the bulb will be light up. Then for the case of reverse bias, because there will be no any electron or hole cross over the junction, because the junction on the okay, so here no carrier movement, there will be no current flow, so the bulb will be not light up. Okay, so this will be the comparison between the forward bias and the reverse bias lah. Okay, so now we go to checkpoint question again. Okay, so students, you may show your answer in the chat room. Okay, so that I know that you understand the discussion we go through just now. Okay, so here the diagram 28 shows a PN junction diode. Okay, so the PN junction diode referring to the depletion layer lah. Okay, so when the diode is in reverse bias, the depletion layer become wider. So what is the reason? Okay, so here just now we also explained already. So we have two type of arrangement or connection of the diode to the battery. Okay, so here you can see from the figure. Okay, so the electron will be here, the red color dot. Okay, will be pulled by the positive terminal. Then the hole, which is a positive charge, will be pulled to the negative terminal. Okay, negative terminal of the battery. Okay, so here this will be cause the current not able to produce because no carrier will be moved across the junction. Okay, so here for the reverse bias, so the electrons and the hole will be pulled away from the PN junction. So answer should be A for students. Okay, so for the option B, C, D is the description for the forward bias. Okay, so where you can see the first sentence B here, the electron from the N type are pulled across the junction. So the N type will be here. So the N type will be have electron. So you can see the electron is able to cross over the junction. So you can see there is a presence of electron at the P-type semiconductor. So this one is explanation for forward bias actually. Okay. Then for the C, so the negative charges flow from the negative terminal to the P-type semiconductor is also true. So the negative charge here referring to electron. Okay, so electron will be represent as a red ball, red dot here. Okay, so here the negative charge will be moved to P. Okay, so this will be same as the explanation as B. Okay, so the positive charge here will be hole. Okay, so the hole will flow from the positive terminal. Actually, it's for positive terminal. Okay, is a positive type semiconductor to the N-type semiconductor. So you can see this have a white color dot at the N-type semiconductor. So answer is very clear. It will be A. Okay, so the next question here, question number 5, where is come from the past question of 2005. Okay, so here, let us read the question together first. Okay, so the diagram shows a circuit consisting of the diode and the bulb. So when the switch is on, so that means we close the switch. Okay, so the bulb does not light up. So what need to do? to light out the bulb. Okay, so here you see the positive terminal of the diode will be here. This will be the negative. Then here will be negative. Here will be positive for terminal or battery. So you can see the positive terminal of the diode is connected with the negative terminal battery. So here it will be reverse bias connection, and the current will be not able to flow through because of the depletion layer is wider, causes the carrier not able to across the junction. Okay, so how we can do to cause the bulb to light up? That means we need to change the connection of the diode or the battery to become the forward bias. Okay, so here the tips here will be diode allow current to flow in one direction. So the question asks us to change the reverse bias to forward bias is actually because the real bias will be not allow current to flow through. Okay, in the connection in this figure is known as the reverse bias. Okay, then so here to change the connection to become forward bias, we have two ways to do. So first, we change the position of the diode. Okay, or we can change the terminal of the battery. So two of the action can change the connection to become forward bias and the current will be flow through. So the A replace the new bulb will be not related. Increase the numbers of dry cell is also not related. Reverse the diode connection is correct. So where is mentioned in the hot tips here already. So disconnect the resistor. Okay, so the resistor is not related to, it's a non-polar device, so it's not affecting the current circuit. Okay, so here the answer will be clear with C. Okay, so students, you may also show your answer in the chat room so that I know you are clear to what I explained just now. Okay, then the checkpoint 5.2, question 6. Okay, so here, diagram 33 shows an electric circuit. It is found that the light emitting diode. Okay, so here the short form will be LED. Does not light up. Okay, so the LED will be with this symbol. Okay, so the LED light up when in what condition? Okay, so here again you can see we have a diode in this diagram. So again the diode will be allow the current to flow in one direction. Okay, so here the LED is actually a polar device. So you can see they will have a positive and negative terminal. Okay, so here the longer leg will be positive, the shorter leg will be negative. Okay, here the positive will be actually here, negative will be here. Just like the terminal position like the diode. Okay, so here the negative terminal connected to negative terminal battery. So that means position of the LED is actually correct. Okay, so now what we can do will be change the direction of the LED, actually the diode. Okay, because here the diode is connected in reverse bias now. So here where this will be negative and here will be positive. So the negative terminal of the diode is connected with positive terminal of the battery, causes the LED not able to light up. So here we have to reverse the pull of the diode. Okay, so answer should be A. Okay, so the LED position is correctly as mentioned just now. Okay, battery also no need to change. So here there will be diode only need to change. Okay, so answer from Jimmy is correct. Okay, I saw the answer from Jimmy is A. Good, Jimmy, good try. Okay, so here the next will be Learning standard 2. Okay, so we have already complete our learning standard 1. Okay, so here we have to go for our last learning standard. It will be learning standard 2. Okay, so the learning standard 2, you need to able to communicate about the function of the semiconductor diode. And then the capacitor has a rectifier. Okay, so here the function of the diode is actually the rectifier. We are going to explain. Okay, and then the capacitor here is actually helping the graph, okay, the current to become smoother. Okay, so you can just go through these two figures later on together. So it will be more clear for you to understand the rectification. So where is the second function of diode? Okay, we are going to explain. Okay, just now the first function of the diode is allow the current to flow in one direction. So here is actually is related now, and we call the function of diode as a rectifier. Okay, so here diode as rectifier. So what means by the rectifier? So you can see the first sentence. Diode can act as a rectifier because it can convert the alternating current or AC as a symbol into direct current. Okay, so the process of converting the alternating current to direct current we know as a rectification. Okay, so the diode able to change AC to DC so that we can know as the rectifier for the diode. Okay, so there are two ways to convert an AC to DC. So here there will be the half-wave rectification. So what is a half-wave rectification? Later on we'll discuss detail. And the second, it will be full-wave rectification. Okay, so the first, the half-wave rectification. So what is the meanings like this? So the half-wave rectification is a process where only half of the cycle, half of the every cycle of the alternating current is made to flow in one direction. Okay, so what means by the half cycle? Okay, so here the first cycle will be here. So this is an input current. So the input current, it will be in AC. Okay, in AC. Okay, so in first half cycle, X is more positive than Y. So here we have X and Y. So here positive and here is negative because of the first half cycle. Okay, so the diode is connected forward bias. You can see here when this is positive and with the symbol diode here, this is positive, this is negative. And this two terminal is connected with same terminal. So this is the forward bias. So that means the current will be flow through. So you can see the output voltage. Actually, this is can know as the output voltage of current. Okay, current output. Okay, so they will be have positive value. Okay, so at the second half cycle, okay, so now you can see. So at the second cycle where I box with red, so now the X become negative and here become positive at the second cycle. So here we mentioned X is more negative than Y. So now the current not able to flow through the diode when the diode is in reverse bias. So here, diode is always, here will be positive, here will be negative. So now you see terminal positive of diode connected with the negative terminal of the source of current. Okay, so here the current is not able to flow through. So you can see here, no any current flow through. So here will be 0. But here will be no any negative half cycle. Okay, because the current not allowed the current to flow through. Diode is not allowed the current to flow through. So here, that means another half cycle, it will be 0. So half wave rectification will be have this definition where only half every cycle of the alternating current will be able to flow in one direction. This will be referring to the first peak here. Okay, so the next will be the full wave rectification. Okay, so what is a full wave rectification? So the process where both half every cycle of the alternating current will be able to flow in same direction or one direction here. Okay, so the arrangement of the four diode here is known as a bridge rectifier. Here we have D1, D2, D3, and D4. So for this, we can know as a bridge rectifier. Okay, so here for the first half cycle, so X is positive, Y will be negative. You can see in the first half of the cycle, X is more positive than Y. Okay, so here the diode D1 and D3 will be forward bias, and D2 and D4 will be reverse bias. Okay, so why? You can see when here X is positive, current will be flow from here, X to A, then to D1. Because D4 is reverse bias, current not able to flow through. Okay, then go to B, will be here. Then go to the DR, resistance. Then go to D. Then go to D3. Go to C, and then go back to A. Go back to Y. So it will be one complete circuit able to flow by the current. So it will be form the output signal, output DC signal. Okay, so here when the current is flow in one direction, so here we know as the direct current. Okay, so here can be also current output. Okay, so this will be the first half cycle. Okay, so another half cycle, so they will be referring to the green color box will be this. So now the X will be more negative, Y will be more positive. Okay, look at the green color box. So the diode 2 and 4 will be forward bias because a lot of current flow through. And then the D1 and D3 will be reverse bias because the current not able to flow through. Okay, so the current, AC current will be flow from Y to C, then to D2, to B will be this flow. Then to DR, to RL, resistor. Okay, then go to D. Okay, and then go to D4, and then go to A, and then back to Y again. Okay, so here will be form the second peak here. So where will be also positive. Okay, so you may see that the both half cycle will be produced the same direction where is positive. So here we know as a full wave rectification. Okay, just that one, there will be only first half cycle will be able to let the current to flow through. Okay, so the second cycle there will be not any current to flow through, so it will be 0 for the half wave. So here will be 2 peak for the V output or I output here. Okay, so here we go for the function of the capacitor. Okay, as mentioned just now, the capacitor will be the voltage smoother. Okay, so the output from the rectification can be smoothed by connecting a capacitor in the parallel across the resistor. Okay, so you can see here the capacitor is connected parallel. Okay, so to the resistor for the connection. Okay, and this connection is a smoothing of the half wave rectification output. So for the half wave rectification, there will be only involved one diode. Okay, so the capacitor will be this lah, where connected parallel to R. Okay, then for the, okay, so here is actually full wave rectification. So here will be involved 4 diode. Okay, so the capacitor here will be connected parallel to R also. Okay, so this is a connection where you need to take care so that the current is able to flow through. Okay, so here during the forward bias connection, okay, so the capacitor will be charging up. Will be charged up, energy will be stored at the capacitor. Okay, so this will be for the forward bias connection. So that means when here positive, here negative, current will be able to flow through. Okay, so at this time, the current will be stored in the capacitor. Okay, so you can see from the graph. So here, this will be the charging position. Okay, so where the positive will be at the top, negative will be at the bottom for the input voltage. Okay, so for the full wave rectification, you need to look at the green color parts. So here will be the charging position. Okay, charging position, where is the forward bias connection. Okay, so then when the connection is at the reverse bias, okay, so that means the input is negative. Okay, so here input negative will be here. So now the current is not able to flow through. So the capacitor will be discharged. You can see at here. For the half wave rectification. And then here, it will be for full wave rectification. Okay, so no current through the capacitor and load. Okay, so the energy stored in capacitor acts as a reservoirs, and capacitor releases charge, or we know as discharge, to maintain the potential different across the load. So you can see here will be the graph when we have the capacitor. Okay, so the dashed line wave will be when they have a 4 diode but do not have any connection to capacitor. Okay, so here the result, the output becomes smoother. You can see here it becomes smoother already compared to without capacitor. Okay, so now we actually finished already all discussion for learning standard 2. We go for another 4 questions. So here the checkpoint 5.2, question number 7. Okay, so here diagram 30 show the circuit for rectification for an alternating current. Okay, so you can see here the source will be alternating current. Okay, so here we have the 4 diode. Okay, so here should be full wave rectification, right? Okay, so which is the correct trace of the screen of the CRO? Okay, so again, students, you may share your answer in chat room. Okay, answer from Jimmy is D. Okay, but here, yes, answer from Jimmy, I think is correct, right? Okay, because here, firstly, we need to consider here we have the 4 diode. where we accept full wave rectification graph. So the first A, B will be out already because both showing half wave, and here B is half wave with the capacitor. Then second, with the capacitor, the output graph will be smoothened. Okay, so here answer will be clear, it will be D. Okay, so good, Jimmy, for your answer. Okay, then the next question, the checkpoint question number 8. Okay, so diagram 27 shows a circuit connected to the cathode ray oscilloscope. Okay, again, which of the following trees is the correct one shown on CRO? Okay, so here what figure should be the answer? So here we have 2 diode. Okay, so here when first cycle, the top terminal is positive, the bottom is negative. Okay, so here the current, is it able to flow through? So here is negative, here is positive. The terminal of the diode is always the same. So here, current is not able to flow through for the first cycle. Okay, then for the second cycle, okay, using the green color. When the bottom become positive, top become negative. Current will be also not able to flow through because of bottom also showing reverse bias. Okay, so answer from Jimmy is B. Yes, answer is correct. Okay, so as per mentioned just now, okay, so the current is also is not able to flow through for both cycle. Okay, so that means there will be no any current to flow through. Answer is B. Okay, so good try from Jimmy. Okay, then the next question, number 9. Okay, so diagram 28 shows an electric circuit which contains 4 identical bulbs, W, S, Y, and Z. Okay, so 3 of the bulbs light up continuously. Which bulb light up continuously? Okay, so here the question asks, we have 4 bulbs here. Which 3 will be light up? Okay, so you can see for the first we have diode. Okay, we have diode. Okay, answer from Jimmy. Okay, wait for the answer. Okay, so first the diode, the connection here will be positive, here will be negative. So this is in forward bias, so you see here negative connect to negative terminal of the battery. So current able to flow through, right? For the diode circuit here. So that means the current will be able to flow through. So the bulb W and X will be able to light up. Then for second, so this is a capacitor. So as mentioned just now, the capacitor should be connected in parallel, but here is in series. Okay, so answer from Jimmy is A. Okay, so let us see together whether it's A. So actually, here the current is not able to flow through because the capacitor should be connected in parallel. Okay, so here will be not light out. Then the last here, this is a resistor. It's a non-polar device. So that means the current will able to flow through for the last one, Z. So answer very clear. Y will be wrong. So answer is B. Answer is B, Jimmy. Okay, then we go for question number 10. Okay, so diagram 1 shows the input signal and the output signal when component X is connected to a circuit. Okay, so here the question asks name or the type of current at input signal. So input signal is actually here. So you can see here is a sine wave. It's a sine wave. So here showing the positive and negative. Okay, so the current here should be alternating current. Okay, then the output signal will be this. Okay, so you can see here we have a peak at a positive. Here is actually moving in one direction only. So the current here should be alternating current because current is moving in one direction. Okay, so what is the component X? So here you can see the alternating current, okay, is changed to direct current. Here showing the half wave rectification because we're using only one diode. Okay, so we are very clear that. So the one diode will be cause the half wave rectification. We're converting the AC current to DC. So X will be diode. Okay, so the function of diode here will be converting alternating current into direct current. So this will be the reference answer for this question. Okay, so now we go for our last question. So here is a comparison question. So we'll be at question number 5 or 6 in paper 2, section A. Okay, so let us go through the question together. Okay, so here, diagram 6.1 will be this diagram. And diagram 6.2 shows two circuits with identical components. So each circuit contains an ammeter. Okay, so ammeter will be here. This is an ammeter. Okay, and one semiconductor diode will be here. Okay, so give one examples of semiconductor material. Okay, so this one we already discussed at our first slide. So where we refer to the periodic table. So we have actually many options. Okay, so the yellow color will be the semiconductor. Okay, so here you can given the main material discussed today. So it will be silicon and germanium now. Okay, so answer, you can just give one of the answer because here is only one mark given. Okay, then B, observe 6.1, diagram 6.1 and 6.2. So here the question asks you to give the difference between the connection of diode. Will be here, diode. Okay, so here we need to look at the terminal of the battery. So the longer one is positive, shorter one is negative. Okay, and then the diode positive will be behind the triangle. When there is a line in front, there will be negative terminal. So you can see the connection. So the terminal positive will be connected to terminal negative. So here we are very clear that the diagram 6.1 is a reverse bias. Then for the 6.2, so here positive, negative terminal for battery. And here positive, negative terminal for the diode. Okay, so you can see terminal positive of the diode connected with terminal positive of battery. So here, this will be forward bias now. Okay, so here the answer, diagram 6.2, 6.1 is the reverse bias. 6.2 will be forward bias. Okay, so the next question, the answer asks you, okay, so asks you to read the ammeter. Okay, so here, this will be the ammeter. So 6.1, you can see the reading or the pointer showing 0. Okay, because in reverse bias, the current is not able to flow through, right? So this will be 0. Then for the 6.2, okay, so here, this is 0. Here will be 1, here will be 2, here will be 3. So the pointer showing half between 2 and 3. So this can be 2.5. Okay, so answer, okay, so here is 0. 6.2 ammeter showing 2.5. So answer, the reading of ammeter will be 0 for 6.1. Diagram 6.2 reading will be showing 2.5 ampere. Okay, so then C, the question asks you to give 2 reasons why showing the different reading for the ammeter. So 0 because there is no current flow through the circuit in diagram 6.1. Okay, so 2.5 showing that there will be a current flow through the diagram 6.2 where is in forward bias connection. Okay, so answer 2 marks. First mark given, no current flow in 6.1. current flow in diagram 6.2. This will be the reference answer. Okay, then the last question, actually got another question. This will be the second last. So based on the answer in 2A, 2B and C. 2B and C, what is the function of the diode in this circuit? Okay, so here, this will be allow current flowing in one direction, right? Here. So to allow current to flow in one direction only. So this will be the function for the diode we learned in Learning Center 1. Okay, so here we go for our last question today. Okay, so the question will be like this. Diagram 6.3. Okay, so diagram 6.3 shows the output signal display on the screen with this screen of the CRO. Okay, so when diode is connected to the AC power supply, we hear. So explain why output signal is produced at shown. Okay, so you can see here, this will be the output signal. Okay, so you can see here we have a peak, then zero current. Peak, then we have a zero current. So that means here, by using one diode, so we have rectification occur, right? So where the AC current will change to one direction current. So here the output is actually showing the DC current produced. But here we have sometimes get zero current. So here is actually the half wave rectification because we're using only one diode. Okay, so 2 marks. So the question asks you why this output signal is produced. Okay, so just now we explained already, because we use one diode, so the production will be half wave rectification. Okay, so answer here, firstly, just how I mentioned to you, so the current will be changes from AC to DC. Okay, so this is the function of diode, where convert AC to DC. Second, current can only flow when diode is in forward bias. Forward bias will be here. Then here will be showing reverse bias. Okay, so during the second half cycle, the diode is reverse bias and block the current. So we produce the half wave rectification. Okay, so this will be the reference answer for this question. So here we have 3 reference answer. So the maximum will be 2 marks given for this question E here. Okay, so that is all for the discussion today. Okay, so before I left the lesson, okay, I want to give you the link schedule for today's lesson. Okay, so you may fill up the link schedule with any email you are available. Okay, so please fill up within 30 minutes after the live complete. Okay, so thank you everyone for joining my lesson today. Okay, so don't forget to follow our next physics classes where every Friday 9:30 p.m. will be for Form 4 Physics, which is for BM group Non-DLP. Then for the Form 4 Physics will be as usual like today. Okay, so will be at every Sunday 8:45 p.m. Okay, so please share my class to your friends so that more of your friends able to gain the benefits from my lesson. Okay, so that's all for my sharing today. Okay, so thank you everyone for joining my lesson. Okay, so thank you also for Jimmy. Okay, so see you again for next lesson. Okay, so bye-bye everyone.